So, the footing around here. Some things example like towels. Well, what I ask myself, where do I need things such as, well, this house, this room, this environment here, what is it, this very right here, is very this, very that here. Here he is. A place to sit here. I don't know what else to say. That all things develop in this world here. We have to think about the different concepts here. Is it just always about some sexual things here, apparently? This is not big case here. It's a sponsorship. I could be increased sponsorship size of different products with I'm as a sponsorship here. Well, do it. Yes, do it. Whatever you do it here. Do those things here. Because I like money. I like power. I like everything here. And then he's when think about visionary. Well, he's some person who's think about the. Well, you always think about things about when you're okay. So, what do you think about the here? World population of 100 billion. If some place like Bangladesh has 2 billion people living, area of I don't know what area is Bangladesh really, but it's not incredible big apparently here. I may be underestimated here. Think about the 150,000 square kilometers maybe. As I say about the Bangladesh population is, if it's around 150,000 square kilometers here, there's 1,000 people average currently in the Bangladesh here. 200,000 here. It's difficult to really say. It was a surprisingly big number here, but it's definitely over 300,000 square kilometers. No fucking way. Bangladesh is over 300,000 square kilometers here. 300 square kilometers is size around here. About the okay, if example 500 times 500 square kilometers is 250,000 square kilometers. 1,000 times 1,000 of course is a classic 1 million here. Square kilometer here. Different countries with the 1 million square kilometers. Mongolia here is one city country apparently 1 million. Okay, let's think about that thing here. The Mongolia, the world cannot support only hunter-gatherers here. And there's no fucking way here. Think about the instead of critically about it here. That house or place, when any country have food enough for supporting hunter-catcher here. If humans had to just hunter and catcher here all the way, that place like a Mongolia show about the society where people don't much like to farm anything here. They still have a farming, but it's more still some pastoral kind of stuff here. The populations cannot really be super big in countries where the pastoral are here, especially hunter-catcher here. Societies here, like a classic old time, where is nobody definitely doesn't no farming, no any kind of stuff here. Okay, so I mean, just think about that thing. There's no fucking way. All animals will be pretty much eaten off here in kind of like a Mongolia here, whereas the illegal fish are. There's of course fish farming, all kind of farming, but in like a Mongolia with this cold, dry, arid place, I mean about it doesn't even suit very well of the farming. It's a surprise about the Mongolian population is around 1 million. So Mongolia is only country whole world here Asia, apart maybe Antarctica, but in the United States here, we have a lowest total population concentration here. And it's no surprise around here. There's more or less total less populous country in the whole world here. In a rate about the human per square kilometer living. So it is the last populated in this respect. It's a crowded country here. Crafted. And it has the last population density of any country in the world here. Antarctica. There's also special regions here where are in kind of like a China. Gobi Desert have a lower rate than Mongolia, of course, but Gobi Desert is not independent states here. Tibet have a lower rate population average than except for even to the Mongolia, but it's not independent states. And Antarctica have incredible love rates area. It's estimated that Antarctica have no less than 200% humans in Antarctica here, which around 100 persons, 150 here, are South Pole Station, maybe 50. Yeah. So Antarctica have only 200 persons, average 150 person whole Antarctica surface area here. Well, alas, it has 150. In 100 years ago, I don't think I have 0 humans. And 150 years ago, human species never was even ever visited, ever in history. Before last 100 years, even to the whole Antarctica here. Humans have never visited in Antarctica before 150. Apparently, perhaps it so knows about here. I wouldn't be absolutely certain. Maybe somebody might have gone there, but apparently he never came back and managed to put history about it, tell about the story where the place it is. So, what means Antarctica has been always been very little human population. So it's no surprise here. It's far away, for at least for me. And it is incredible cold place here. It is very, 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 very unsupportive of human species here, I guess. I'm looking for ice age here, is the era of the coldness here. It's either about that because the huge amount of world oceans will be frozen around the poles. It is either about that indeed that because sun activity that the average temperatures will be eventually, maybe not now, next million years or 10 million years or 100 million years, but the beginning maybe after a billion years will be rising so high this year that there definitely won't be any surface ice whole Earth planet here anymore. After maybe 1 billion years, it's estimated that the temperature will be so rise sun activity here that there won't be any surface ice whole Earth. If there will be ice now Antarctica and a pole areas in polar regions, temperature increase will be estimated at especially 1.5 billion years. There is no fucking a single ice anywhere whole Earth. After 2 billion years, it is estimated about that it's gonna be a long period of time. It is estimated that over 3 and 5 half billion years, when the sun will be eventually just keep warming and warming and warming. It's gonna be a long period here. They only estimated that the Earth have only around 1.5 billion years era of the human population. Yeah? So in the next 3.5 billion years, before the sun will be eventually 5 billion years, will be the finito, this current position, before it will be eventually destroyed, mostly the total mass will be the final phase of its current form about here, its current normal star, also call it okay, so the stage around here, when it is able to produce life supporting about its activity toleration, before it will be the next stage around the sun here. And that means there will be much more total time the sun and how the Earth is inhabitable here in respect here. So it is said about the 500 million years ago now on, there might be still easy habitable, but the temperature will be gradually rising about the, maybe not today or even 100 million years ago, but within the billion years of the now on. It might be start from 700 million years, and the temperature is rising by degree about here. Eventually the temperatures would be decreased. So what do we think about the average temperatures? It's said about the, for 500 million years now on, the average temperature will be rising only about maybe 5 Celsius here. That is not much based on the solar activity here. Everything else, the air will be a little bit cool in itself, but eventually the average is calculated about the 5 Celsius more average temperature. So next 500 million years is fully easy. This everything will continue. It's a great. Things gonna get more warmer, and that's mean about the average temperature the whole world wise will be 5 Celsius. If you live in an area where temperature is now 50, you always have 5 Celsius more over here. However, temperature should be rising about the 25 Celsius in the next 1 billion year, okay, so it will be really gradual. It's bigger slowly here, but then it will be a little bit faster, right? To pick a clip up here. Let's say about that, maybe the temperatures average 25 Celsius higher than they are now in billion years on here. So humans' life and world life superation become a little bit more problems. So Especially if you're looking for the organic chemistry here, okay, so the increase in temperature around 25 will be giving, example now it's 5 Celsius, will be giving 30 Celsius. It's quite a heavy temperature right here, but still perfectly survivable by human beings. But other places like a Sahara, well, but the whole life will be minimum skeleton around here. In the case here, some rainforest it might be surviving and it might be keeping cooling here, but with the enormous temperature, the rainforest will be itself, I guess it will be destroyed about the here. Enormous temperature regimes here, and unable to stay more enough surviving of the enormous temperatures, and the water temperature will eradicate about the here. Rainforest might be 30 Celsius, and current chance will be increased to the 55 Celsius, which is too much occasion, unless some kind of an organism able to better shield themselves from heat and have a different kind of organism, more especially we talk about here. And when looking for the question here, from 1.5 billion years ago, it's expected putting all up to 100 Celsius increase about it from now on here. Well, that is a huge increment of average temperature, 100 Celsius from 1.5 billion years. This is said to be a limited point here, that where it's expected all the life on Earth will be getting inhabitable whole Earth here. It is estimated because 100 Celsius is estimated temperature here. So this is what I think about this thing. If things are now here 5, it will be 105. You will ask looking for, well, pretty much most of the water whole Earth will be evaporate off the case here. Well, of course, in the air crown the case it's possible. There's always habitable zone case within air crust here case, and let's face about this thing here. So, example, shielding around from air generation. So polar regions especially in 0 degrees, because as extra tilt every area in the whole world will be given off. Also the temperature will be. It's possible still, of course. We here are clowns to finding out here. Already said about that the temperature will be keeping rising 150 Celsius maybe, around 200 Celsius, 150 Celsius here by 2 billion years. And it's said to be 500 Celsius by 3.5 billion years on. In the period with the last 1 billion year, the temperatures are estimated to be about the no less even approaching thousands Celsius here. This is a moment when the air crown many elements will be completely evaporated here, I guess. Vapor that will be gaseous. You can think about the all oxygen will be almost uploaded off the whole Earth as a gas here. A gravity. So here's some of the Earth different things, yeah. Things like a garb of the atoms here. Various degree about here, depending materials, will be gaseous. The first thing about, of course, things are like oceans will be all a long time gone here. There's no way the oceans can survive the thousands of Celsius temperatures here. It is said about that the sun is expected to destroy whole Earth's surface around here. Not only surface, but perhaps annexing here. They're looking for the sun, which will be expanding enormous rate from 1 million kilometer radius to all up to maybe 160 million. So kind of a maximum average, okay, so the sun radius here. So it will be 160 times more bigger than it currently is the case here. Okay. Or the sun will be almost exactly the same mass nevertheless here. Marginally increase the mass because some will be even losing about even the sun emits light and then thin some material. But some will also can about the here gravitationally will be one solar space, another kind of a intermetal medium here. So for 5 billion years on the last 500 million years, the period when the sun will be really become a red giant here, I guess. This is a place about when things really increase here because the gas gas stars around here, the gases with the gravitation here, there's something like a sun here, the bubble here. What happened? The gravitation is very big thing here, but apparently it can be overcome everything. Especially big hits can push things apart here. Okay, so when the sun is made of the sun's very soft and lightweight of the molecules hydrogen here, even the hydrogen, even the gravitation, the hydrogen atoms. Okay, so because they are so lightweight, okay, so even they are still able to bond about it with the gravitation. There's no way, except for some moon, except for able to bond in the gravitation hydrogen atoms. They have so enough kinetic energy, hydrogen atoms, that they easily will be just get the escape from a moon atmosphere if the moon will be any atmosphere. The same goes around here. It will be good to those hydrogen atoms here. In some stars like sun here, they're still bound about them. Okay, the big important factor recognized about the solar gravity here remains same pretty much here, but the distance here is in some far away, like where now Earth is from Sun here, the gravitation is enormously diminishing of Earth here. Even the gravitations have an incredible small drop down in a long distance here, because when the distance double, gravitation only half here, and that's the interesting thing about here. If I go example one distance gravitation, here is a gravitation. Everybody wanna learn gravitation. If I have example 1 kilometer away from object 1, and gravitation is 1 here. If I go 2 kilometers away, the gravitation have a half it here. So you see for a factor here, like this thing here. So there's only half of the gravitations here. Well, that's interesting about the gravitations only halving per distance here. Okay, so if I go 3 kilometers away, what has happened now? There is now anymore around of a 33% of the case of gravitation, and 25% of gravitation of the 4 kilometers away here. So there's only more around 25%. But this is those spots around here. If I go example 8 kilometers over or 10 kilometers away, if I go 10 kilometers away, there will be 1/10 of the gravitation left here. Okay, so still quite a lot of gravitation after all. 1/10 of the gravitation than what was the first kilometer. It will be 100 kilometers away. There will be 1 of the 100 of the gravitation anymore effective original gravitation. So gravitations at this kind of linear drop down here. Okay, so not exponential important factor recognized, but as we already thought about recognized, gravitation have a directional proposition distance, a linear drop down here. There's other important factors here, as I say about it here. The reasons why black holes can be more specular is the fact about it here is a gravity. So okay, so a gravity only halving through the distance here. When it 2 times farther here, they will be gradually cubical here. In the lab, the gravity will be only halving around here. They will be dropped down of the cubical method here. Okay, so example here is the gravitation. There will be 9 times more in a 3 distance, when there still will be alone of the half of the gravity here. Okay, so left here. So what mean about it here? The black hole with the 1 billion solar masses will have a radius of the Schwarzschild radius. Who knows what is the distance? How many million kilometers? I don't know. Or 1 billion solar mass can have estimate being over 200 billion kilometers of the Schwarzschild radius, which is usually also take so kind of a horizon of a whatever you call it, event horizon is the word. And that means about that if it will be example distance here, it estimated that 1 light year is about the 800 trillion kilometers here. Is this actually distance was here? When you think about the 1 billion solar masses here, How is it calculated about the event horizon here? And this kind of object here. But the funny thing about this kind of object multiplication is that even if we have 1 billion solar masses here, okay, so this object here is the total volume will be still mean about it is lighter than have a lower density than extrapolated here, okay, so total density is very good question here. The black one to think about it when it's the black hole. A black hole is not event horizon, okay, so event horizon is just is ulterior some kind of zone about it here. Like a creation, it's black hole is the circle of the physical phenomenon in the center of occasion. There are those event horizons. Event horizons is just a kind of a gravitational orbitum forcing about the things itself to that core here. So that's what made it a black hole. Okay, so if you're looking for rotation here, the black holes here. If you're looking for what black holes, bigger the black hole is, what we know about here, is the more volume is wasted around here for so for the nothing here, I guess. What is the volume really is black holes here? We don't think about black holes here. We think about black hole actually. If you're looking for one atom here, it have like some of the classic treatment here. Here's the atom here, the proton. Even the size of one sugar grain. One grain of a sugar example of it will be one proton here and one grain of the here. If you're looking for hydrogen atom here, so we're looking for one single proton atom. It has one single proton here. Okay, the distance from this to the electron, okay, so will be no less than 200 meters here. It's one grain of atom here is 200 meters are the electron distance away from here, and totally it will be have a 500 meter radius of this case, and hydrogen atom with this will be have as a kind of a so-called of the high force will be operated from here, call it the electroweak force. The drop down is very serious after 1 kilometer. That means the electroweak force come like exponentially in the case to this distance here. Gravity is pretty much only force that doesn't drop its force by distance exponentially here. And that's interesting. Look at gravitation. This is to operate quite a different for other forces here. Gravitation force is small in small distances here. Forget about the here enormous masses here, okay, so no less here. So that's interesting for the gravity is different on the forces here. Okay, it depends on how much you have mass here. If you have not much mass, okay, so gravity is very irradiant important. 1 gram of material for a perfect vacuum of the universe nothingness would be have no really much gravitation effect anywhere. If we're looking for here 1 gram, we have this kind of a spares of 1 gram here, and we're looking for 1 centimeter distance in a universe of nothing here, environmental. Well, the gravitational force between these two balls is incredibly small here, okay, so it can be measured about here by the function about the total mass g gravitational. So what does it mean about here? The gravitational acceleration between those two objects is less than 1 in a quadrillion, okay, so per year. Less than 1 quadrillion meter, 1 quadrillion of the meter here, or minus 15 okay, so meters per year, okay, so the acceleration speed here. That's not much, okay, so if you're looking for seconds, it's more like a 1 in a 20. In perfect, let's go to 1 in 20 minus, okay, so minus 20 magnitude like here per meter per second like, acceleration here between these two objects here. It's quite a lot of occasion. So when the final will be eventually after maybe a couple trillion years, okay, so these two objects are here in this kind of thing because they haven't no any distance going iteration will be each other, maybe case so getting close to get Naxia, okay, so it will be minuscule, okay, so think about this kind of idea about here, the black holes, okay, so if you have a black hole here, okay, so if it will be black hole, might say, so this will create black hole just next to myself, in front of here. What really happened is black hole, okay, the acceleration will be speed of the light up, and all the material for me will be accelerated towards the speed of light in this black hole towards it here, because of the mass in this black hole compared to the mass of this 1 gram object. In this case is over 35 magnitude bigger here, okay, so 35 magnitude bigger, because the mass of this black hole is 35 times more, 34 magnitude of the time more here, because you have 35 times more total mass around here, this black hole, than this here down here. So whenever we introduce this thing here, I said about the landing about, I mean, there will be so smooth landing, but there will be absolutely no effect really, this gravitation around here. Because the gravitation is so incredible here, okay, so the both object will have no effect of the gravitation, and they don't displace itself, okay, here. So the gravitation effect is small about those atoms, and it will be matter for those atoms, example. When it will be both will be eventually after trillions years, maybe, okay, so just managed to, okay, so emerge together these two balls here, and never leave, because there's no pressure effect here. Sure, we will looking for that it will be affect, not nature of those spheres atoms here. No matter what this make, it will make a of this something like a very material with have absolutely no whatsoever any kind of a the speed is still small. That will be have no effect whatsoever here. Well, this equation is just mind game here. This is but the gravity has really slow here, but only with the very small mass here. Well, when gravity is a really big problem is when there is enough material, enough small space here. That's interesting here. There is a said about here that it's possible to create black hole for any object, no matter how small object they are. So far that you can upper get in how small space those things. What means interestingly here. So let me ask about what is the Schwarzschild radio for things like proton here, guys. Is it calculated that a proton have an electric voltage, and it is 1 billion times more than one proton itself, okay, so is the case. So you need to have a protons here. In order to create black hole, you need to be getting 1 billion protons, okay, so the one proton size, and somehow able to push them together here, okay, so it's quite a difficult task around here, but it's entirely impossible here. You need only 1,000 protons of the 1 billion protons, and percent the size of the one proton, and suddenly you will have a Schwarzschild radio about here. What will happen is kind of incredibly small black holes, okay, so they will be more quicker lose about it, and they will be gaining about it here. It will be very short time here, it will be lasting for a couple trillion of a second, and will be vanishing and will be exhausted itself away here apparently. This kind of black holes unfortunately cannot gain mass here, guys. So only black holes that exist in actually this universe really any more than a couple trillions of the seconds are black holes often make for massive stars here, okay, so even object like Earth can be compressed as a black hole here. However, it's kind of difficult here after all, as you say by here. So the black holes of the Earth size, okay, so total mass, okay, so kind of lasted maybe 10 years around before it will be black holes of the Sun size will be able to take a maybe incredibly much more size, okay, so over 15 after trillion years, okay, so able to exhaust it. The black hole of the size of the entire galaxy will be taking of a 28 magnitude here. The black hole of the universe is expected to take it over Google years to able to exhaust it, maybe 150 magnitude activation, because Google is magnitude 100. Magnitude 150 before they are able to evaporate those black holes around here. It's interesting looking for here that the bigger the black hole, more its mass is, so more slower they lose the total mass around here and total size around here. It's a reason for the biggest, most massive black holes are also most stable here, and most smallest black hole. If I will be compressing myself with black hole, my mass, I guess, it will be lasting maybe couple microseconds around here. But it will have enough mass, okay, so to able to ever become bigger here. What is the minimum black hole, okay, so that you're able to get a black hole which is able to have a stability, have able to gain enough mass to able to continue the process to become a bigger black hole? It's questionable here. But it's estimated to be around maybe 500 kilos mass here. What does it mean about the you're able to create a black hole with only 500 kilos of material here? Incredible here. So, is it possible this kind of macro, given all the material already, it will be bigger feeding and will be eventually consume everything around? If you put in Earth black hole, okay, so microscopic black holes are too slow. It minimum have to be estimated to be at least 20 kilos of the mass around the black holes in order to be able to that they did not immediately extinguish themselves around the table to make a gaining mass here. You have to be immediately. It's possible, however, some things like a uranium here. If you take a black hole, okay, so there, and put in some very density material like a plutonium here, okay, so around here, some plutonium core here, okay, so you would be shooting plutonium this black hole. So there's a black hole with its only mass of the 10 kilogram here, but you will be almost light speed, okay, so towards the way of plutonium. Suddenly this will be quite a fast location here. It will be thousands of kilos of plutonium, okay, so you will be feeding about this black hole location here. It's possible this black hole will be really grew up very fast location. So it is possible to have even in this hydroscopic theoretical sense, black hole even only couple 10 kilograms of enough big here is able to alone by good sufficient feeding mechanism of this case, because it needs incredible fast case and feeding here. And when the black hole is 1000 kilogram case in here, putting some surface like a Earth case in here, well, what it will be do, because of gravitation here, it will be immediately case getting through the whole Earth surface case cutting it will be take like a few seconds plastically in this respect case. There will be just getting through about the Earth center here. And when it's the Earth center, this black hole case, well, that's quite a bad news for Earth itself, I guess. You replace the whole Earth center, I guess, with black hole, I guess. Because all center, everything stand whole Earth, I guess, towards this one single center, I guess, thing here. All mass whole Earth, I guess, stand for this center area here, I guess. Well, however, the whole Earth stand in a black hole, I guess, it doesn't work very well here, I guess. Eventually, everything will be very quickly, I guess, it will take a long time, okay, so we talk about a couple seconds, okay, so well, whole Earth will be actually, in this situation, will be just dropped down, just directly to black hole, okay, so yeah. And the process wouldn't take at all long time, because there's no motion outward here. So a few minutes, okay, so if you will be putting a 1000 kilogram black hole in Earth center here, it will take him 5 minutes to whole Earth will be, okay, so drop that black hole, okay, so that's a fact about here. That's how this physics and science count about here. If you will have a black hole of the size maybe about the weight about maybe 1 gram, it's not enough, okay, so here. The Earth case and even Earth center here. It's estimated about it perhaps be around maybe couple 10 kilograms at minimum here. Then I got a problem here. Because of the enormous pressure towards that black hole, there will be feeding mechanism here. And well, Earth doesn't have a, because constantly when the black hole will be always things will be pressure toward it, will be automatic feeding here, okay, so. And that's the problem here. Especially on a black hole in the center of the Earth here, okay, so. They constantly all the surrounding material will be dropping towards it because gravitation. What makes black holes so dangerous is that gravitation is so fucking big deal in the long distances here, even short distances here, too. But it takes a lot of material here. The most important factor of a black hole is a mass here, okay, so. In a universe with a long distances and very marginal masses, the black holes wouldn't be ever a case around here. If I mean the mass forces of a universe, okay, so a couple milligrams of the material as sugar grains in the whole universe, okay, sure, will be never existed any kind of black holes in the universe where conditions are the same like here with that maybe even 1 kilogram stuff around here and there, okay, so. because those 1 kilomicron matters would be never compressing in the Schwarzschild radiation here. Even if somebody say eventually the gravitation will be pulled together all the material, so far, okay, the total mass of the universe is much less that they will be ever able to press it together. Think about the universe. If the universe would be weighing 1 kilogram total here, we can calculate any universe, okay, sure, where the total pressure is not limitations here. A universe with the mass of the Earth will be never compressed to black hole, okay, so unless some force able to really forcing energy here. Gravitation will be alone never able to even make a black hole, okay, so an Earth here, okay, so Earth alone don't have nowhere enough the total gravitations here. Neither have sun here. It's a massive object like a solar here. Sun with maybe 5 solar masses. It would just have enough mass to able to compress the black hole, okay, so yeah. Just and just here. Neutron star. I mean the process began here. And stopping here. To say the material of the black holes is questionable here. But it's it's or a very dense matter all far here. So why the gravitations here? It's about the here material. It's all about the mass. Is most important thing about the here gravitations here. Gravitations work only for a big mass and big distances here. Distance is not important, but masses are more important for gravitations here. Because as I say about here, in a universe with a minuscule masses here, 1 kilogram masses here, well, material still can be eventually found each other. However, the effect is the relativistical distance between different materials, which will be getting the way how the materials are expressed. It will have an effect about the formations, about the how they really function, these objects themselves here. Because gravitations need a lot of mass here, okay, so gravitations need a lot of mass here, but that's one thing, right? Gravitations need always a lot of mass. That's what we know about here. In the enormous amount of mass to able to gravitations come really important force here, okay, so and gravitation, especially in a mass universe with the milligrams of application here, is so little that the gravitation would be hardly ever existing in a visible force, because there's not really any shown about the gravitation topic. Because objects will be not really spinning each other, I guess, in a few milligram scale here. If you're looking for a sugar, guys, they won't not spinning each other or anything like it here. If you look at the spin, is more driven about the initial conditions around here, I guess, make things spinning around here, orbit or whatever here. If you just drop it without any kind of velocities around the universe, any kind of momentum here, starting momentum, you're looking for statistically putting here, universe will be never static anywhere. But if you're looking for this kind of a static for a beginning, the first condition, this gives same rules as universe here. And the object will be just drop to each other, will be in the center here. But in this kind of a total universe with the milligram, if you put 1 trillion light year away of this 1 milligram sugar grains are here about the data here. We look at the universe with 2 sugar, what is 1 milligram here, okay, so it's questionable those gravitation haven't dropped down here. 1 trillion light year is enormous. It is still said about it here. I don't know if this is another physics force it will be exist here. It is said about the gravitations have an infinity range here. Even there's infinity range here, the speed, how much okay, so per example per year, okay, so here, acceleration between those gravitational objects can be calculated. It's maybe one of the 250 minus 250 meter per year, okay, so here, acceleration. Yeah. So it will be take maybe around figures the distance here, okay, so. Remember, things always accelerate, so they will be always, first they start like a 0 speed here. There are 0 speed velocity, but eventually the speed always increase, closer they get together, is a stable drop down here. There will be the kinetic energy will always just will be increase about here, okay, so, And the kinetic energy is always the highest just before object will be finally will be basically the first and so-called touch here, I guess it will be first hitting each other. So I don't know, but here the speed still, I guess this object will be. It's interesting to say about here, if you put two objects like this here, it's very far away here. That's because of the acceleration here. It's much more acceleration of the, if you will be putting enormous distance away here, the speed here, because they will be eventually accelerate towards here, because the first acceleration here, but because the gravitation is so weak around here, this object is the acceleration still just sucks around here. The acceleration will be not much, okay, so even the acceleration per second more here, okay, so more and more and more. It's still okay, so it's difficult to really say about what the final speed of this object will be. There's a kilometers per second here. Even the incredible small object, okay, so here. That's interesting question about here. In universe, I guess, because they have gone so long distance, okay, away from it here, I guess. If gravitation have no cut down here, it's like, because of any distance here, we're looking for extra kilometers here, or light years. We got a light year, magnitude of 500 light year, okay, so now that is incredible, okay, so distance, okay, so okay, magnitude of 500 light year away here, something like this, if we do Zucker cranes like this, okay, so they still exert, okay, so by the radius of the 500 magnitude the distance, of course, decimated away the gravitational effect themselves here, but the acceleration here, okay, so this case, the gravitation can be of course calculated too. So the funny thing is about here that the total kinetic energy by those objects will be so much faster. The total impact will be hitting if they are putting as far away from each other as possible here. Instead of just right next to this, we'll look at this object 1 millimeter away from each other. Zucker cranes around here, and back up with gravitation here. It will be still take who knows how many trillions years of those Zucker. But they will right to next case, the gravitational effect is so small as objects, it will be maybe take trillions years to hit each other when the final will be a boom here. But if I put this object here, so this the speed about before it hit it will be something like a 600 minus 600 meter per year, okay, so here. Minus 600 meter per year, okay, so here. Or 598 millimeter per year, or distance here. So this is the case here. That's the acceleration speed. Or the total speed, not the acceleration speed, but the speed around when they were hitting around here. Minus 599 magnitude here, meter per second, meter per year here, okay, so speed. It will be minus something like a 620 meter per second here, I guess. And if you suppose how slow is that here, okay, so if the example would be, if we use this speed example, one travel a distance, for example, of one single example for well, what is the distance? If you have example this case on here, from proton to electron here, it will take still like I said over Google year, okay, so here, then we get a travel here with this speed here. There is still like a Google year with this speed, okay, so yeah. So that's the acceleration is so low about these two axes, okay, so remember the gravitation is so much stronger on, okay, so this distance, okay, so slow distance, the speed will be much faster initial acceleration. Remember, more closer your okay, so object axis will be always increase here. Because it's no static acceleration here. The same I had to say about for any acceleration towards any object. If I example are 10 times more faster object than 1 time, and the acceleration is always lower for further away your object. Its acceleration is direct condition dependent here. So if example are 100 magnitude light year away from example object for any object case here, the access towards that object is of course incredible much lesser case than it will be just next to maybe 100 kilometer surface. Example Earth here. If I look at universe nothing else than Earth here, it will be 100 magnitude light years away here. I will accelerating around maybe, because half time here, 100 magnitude time slower acceleration speed than will be accelerated if it will be maybe 100 kilometers away from Earth's surface here. So the acceleration is like here First of all, it will be, of course, will be almost like a zero all the time here. Okay, so it will be very small fractional number over zero here, like a magnitude of 100. Okay, so minus 100 meter per year. Okay, so here the speed, or 120 per second meter per second here. But eventually the speed will be increased basically here. So it will be take, of course, Google years about where before I enable to this station here. So it will take maybe 800,000 magnitude years about it, but eventually we're hitting this Earth. Okay, so actually so will be the final like a couple thousand kilometers from Earth here, 1 million kilometers away from Earth. The acceleration really increase about the year. The funny thing about an acceleration towards the Earth is that it doesn't matter actually how far away I am from Earth here. When I talk about this acceleration here, my speed towards this Earth actually is pretty much same here. Okay, so here, do I drop just there or 1 billion years away here? It's important factor, okay, gravitation. So I would have been accelerated towards light speed here. Because it's this stationary here, I never gain amazing speed here, okay, so yeah. If I have a long distance time to accelerate, because my acceleration is very slow all the time here. So I only accelerate very fast when I'm close to object, I will be increase this acceleration. That's an important factor, we make a huge assumption mistake about here. Of course, this is the way about it. That's mean about the here, it makes no fucking difference. It will be a given acceleration advantage about the billions years, or it will be just jumping right off the Earth atmosphere. Okay, so but we have the same kind of a speed no matter what very soon approach speed about the here, or the second acceleration speed will be achieving the situations here. So that's mean about this Suzuka base putting Google X years away. It's about Google light year away from it, so it will be never speed of the light year speed of the case. Well, we'll be just finally coming together, okay, so finally they will be having just marginal speed, pretty much the same. They will be put next to each other, those objects here, because X is about the time doesn't mean nothing here. That's a funny thing about here, recognize here. There's no super acceleration here, because there's no gravitation magnitude here, okay, so let's go to Bangladesh here. Bangladesh. Sleeping here. What is Bangladesh? Maybe I started calling about that. I should be